This is Yeon Jo and Suyeon Yu from South Korea. It is our pleasure to be here speaking in front of you all. Today we are going to talk about our paper Power Savings Integrated Task Scheduling. Our presentation will take place in the following order. Our target is a system that has real-time tasks and interactive tasks together. For example, smart cars have real-time tasks with strict deadlines such as the engine, sensor recognition, and at the same time they have interactive tasks performed by users' input. In the past, it mainly scheduled two kinds of tasks each. However, recent attempts have been made to integrate them and schedule them on one system. In addition, these systems mainly use limited batteries, so power saving is one of the most important topics. Therefore, we propose a DGIA that can schedule real-time and interactive tasks together with power saving. There are three main goals for our research. The first is to satisfy the deadline of real-time tasks. The second is to ensure that interactive tasks have reasonable response times, finally saving the power of the system. Our method can be largely divided into three parts. First, virtual real-time tasks. For interactive tasks, we use the notion of a virtual real-time task that reserves the resources for sporadically arriving interactive tasks. Offline scheduling is performed first for periodic real-time tasks, including virtual real-time tasks, and the system is executed based on the predetermined schedule for real-time tasks. If interactive tasks arrive during the execution, they are allocated to the time slot of virtual real-time tasks. The ER pair algorithm is used for offline scheduling as it is known to be optimal in multi-core real-time scheduling, and round robin is used for the scheduling of interactive tasks. Second scenario. One of the things that make our problem difficult is that we don't know a lot of interactive tasks at all before scheduling them. Therefore, it is difficult to predict how current interactive task execution or application of power-saving techniques will affect the future. We wanted to solve this problem by assuming a set of virtual tasks with different utilization. We call this a scenario. Here, the utilization can be matched by a lot of interactive tasks. In actual scheduling, we track the interactive task load just before and schedule the system by selecting one of several scenarios. This is possible because real-time scheduling, including virtual tasks, is offline. Finally, power-saving techniques. First, we use dynamic voltage scaling called DVS. Based on CMOS digital circuit technologies, power consumption is proportional to the square of the supplied voltage. So lowering voltage can save processors' power consumption. Next, we use hybrid memory, which uses low-power non-volatile memory also with DRAM. A non-volatile memory such as PCM or STT-MRAM stores data without refreshing, so it is good to power saving, but its access time is relatively slower than DRAM. So such techniques increase the execution time of tasks. It possibly results in the deadline misses of real-time tasks. Thus, we need to decide power-saving configurations for each task without deadline violation, which is an optimization problem known to be NP-hard. So we use genetic algorithm to optimize them.
As you can see from the left, before scheduling, we first generate several virtual tasks that have different utilizations, and then run the genetic algorithm about virtual tasks and real-time tasks to decide power-saving configurations for each task. And finally, multiple scenarios are created as a result. During scheduling at each period, one scenario that best suits the load of the interactive tasks is selected and scheduling is performed in this manner. That is, real-time tasks and virtual tasks are scheduled with ERFair, an online scheduler, and interactive tasks are scheduled using round robin, an offline scheduler. We evaluated how good our methods were through simulation, and this is the experimental condition. First, we assumed a multi-core environment using 4-core processor. Second, we set the utilization rate of real-time tasks and the arrival rate of interactive tasks as variables to consider various environments. Third, we applied power-saving technology. In detail, 4 discrete DVS modes, 2 types of memory, and genetic algorithms were used. Finally, we have a control group, what we call original, that does not use both of the virtual tasks or power-saving techniques and compared it to DGIA. First, we created a set of tasks for our simulation. Real-time tasks are created based on 4 target utilization rates, and interactive tasks are created based on 2 target arrival rates. This demonstration video shows the task creation process. First, we generated real-time tasks. Next, we generated interactive tasks. Next is about generating virtual tasks and scenarios. When the power-saving techniques are applied, execution time for each task can be newly calculated. So the scheduling feasibility is checked through equation 1, where m is the number of cores in the processor. If 1 is satisfied, the deadlines of all real-time tasks can be satisfied through p-fair scheduling. Meanwhile, as a system resource must be reserved for virtual tasks, equation 2 should also be satisfied. So we generate virtual tasks using that equation. In addition, they are created in a minimum number within the range that satisfy it. The picture on the right shows that we created 5 scenarios for a specific set of real-time tests. Final part of the implementation is about genetic algorithm. The role of the genetic algorithm is that real-time tasks and virtual tasks can be executed in power saving without violation of deadlines. So it predetermined the processor and memory mode of each task before execution. To do this, we decided on the encoding. We used 2 strings to express DBS mode and HM mode of each task respectively. Second, we evaluated solution based on power of consumption and applied penalties to solutions that violate deadlines. Third, we used roulette wheel selection method to select solution. In conclusion, we found a solution that has low power consumption and does not violate deadline. This video shows generation of virtual tasks and the process of genetic algorithm. As in the graph on the right, the solution converged as the evolution was repeated. This is a video of scheduling simulation. We printed it out to the console so we can see information about the task every period. Next is the result of our simulation. To begin with, we confirmed that the proposed algorithm DGIA has an average power consumption of 23% lower than that of the control group. And of course, you can see that the less the task load, the more power savings. On top of that, we confirmed that the response time of interactive tasks is reduced by 3 times on average. The graph below shows the change in response time for simulation time in a very high load environment. Finally, this is the expected contribution of our research. Our research will improve energy efficiency in the Internet of Things and cyber-physical system environments. Also, it could provide the responsiveness of interactive tasks in autonomous vehicles and intelligent robots. This is the end of our presentation. We really appreciate your attention. Now we would like to invite any questions you may have.